Okay, so far we have discussed the effects of wires to the circuit. So we have discussed that because of the wire, we could result in the delay, and we could result in the consumption of energy. And then we have said that the most prominent effects coming from wire are the R and C, the resistance and capacitance. Okay, and actually, there's another effect related to the wire, which is the wire induced inductance. Okay, so that means if you want to have a more accurate analysis related to the wire, we should include the wire inductance. Okay, so for example, as you can see in this slide, originally we model the wire to include the R and C, the resistance and the capacitance. Okay, and actually, if we want to improve the accuracy of this modeling, we can include resistance, capacitance, as well as the inductance. So you can see this. We can include the inductance. Okay, and because of the current flow through the wire and apply with the inductance, we can result in a change of the voltage. Okay, so in the bottom of this slide, we show a simulation result. For example, if you only include the resistance and resistance and capacitance, so you will end up with getting this curve. Okay, so this is called RC, resistance and capacitance. But if you include the inductance into the modeling, so you can have this dashed line, then you will have this RLC curve. Okay, so that includes a more accurate component when you analyze the effects of wires. Okay, so that concludes the discussion about the wire. Okay, so as we said that the wire could result in the delay, power consumption, and noise, the crosstalk. So there's an idea we call wire engineering. So that means we can purposely design the wire, like the length or the routing of the wire, to achieve the goals such as the system delay, the complexity, which is area, and power consumption. We end with the acceptable noise, the crosstalk level. So we usually call this, in general, we call this a wire engineering. So we try to achieve the goal of delay, power, and acceptable noise by specifically design the wires. Okay, and what's the degree of freedom? I mean, what kind of stuff we can design on or based on the wires? So include like the width of the wire, the spacing between two wires. Okay, and we can have the how many layers we have in my circuit, and we call the wire shielding. So how do we place the wire to reduce the crosstalk, which is to reduce the noise between two wires. Okay, so this is a rough idea for you example that in different wire spacing, you can see in different wire spacing, the pitch versus the coupling and the pitch versus the delay. So if you increase the pitch, that usually means you increase the space between two wires, then you basically reduce the delay and you reduce the coupling. So that means we can play with those design factors like width, length, spacing, layers to control the delay and the complexity and the power. Okay, but as you can see that if you increase the pitch, actually you increase the area, right? Because you need more space between two wires. So it's gonna be a trade-off between space and the delay. Okay, so as you can see from this curve. Okay, and another technique we can use to control the noise is called the wire shielding technology. Okay, so the idea is to use we call the wire shielding technology to control the crosstalk. So for example, we can increase the space between two adjacent wires, okay? Or we can shield wires. That means we put some special material between power and ground lines, okay? So for example, in this diagram we show A0, A1, A2, and A3 are wires, okay? So we can shield on one side. For example, on one side of the A0, A1 is VDD, another side is ground, and then you still have crosstalk between A0 and A1, right? And we can also shield on both sides. For example, this is wire, and on both sides will be VDD and the ground, so you don't have the crosstalk between A0, or you reduce the crosstalk between A0 and A1, okay? And you can also have the like interleaf, like A, B, A, B, A, B, like this. So bus A switch on clock rising edge, bus B switch on the clock of falling edge, so they don't switch at the same time to control the crosstalk or the interference between two wires. Okay, so these technologies are possibly used to control the crosstalk, and that means we control the interference between wires. Okay. Okay, and then finally, we have some topics. Although those topics are quite important, but just for your information to know. Okay, so as we can see that the R and C are proportional to the length of the wire, which is L. Okay, and the RC delay is proportional to the L squared. So L represents the wire length. Okay, so you can see the length between two components, the wire length. Okay, so then what we can do is we can break the long wire into n shorter segments. So for example, in the button, we just break the long wire into n segment. Okay, and we drive each one with a signal amplifier. We call the repeater. Okay, so to control the attenuation or the delay of the signal. Okay, and another thing that is usually needs to be considered in the circuit manufacture today is called the variability or the variation. Okay, so the variability or variation, that basically means if your circuit is designed and implemented, there are some other factors that might also result in the change of the behavior of the circuit. Okay, so for example, we have majorly two categories of variations. One is called environment variation, including supply voltage and the operating temperature. So for example, if a circuit is manufactured assuming the temperature is like 25 degrees Celsius, which is the normal temperature. However, if you are practically operating this circuit at a very low temperature, like let's say 5 degrees Celsius, so then the operating environment might change, right? From 25 degrees to 5 degrees. So that's the environment variation. Okay, the environment change. Okay. Another variation is when you process or when you manufacture the circuit, you have the variations related to the process, like the threshold, the channel length, and the interconnect dimensions. Okay, so the circuit must be designed and manufactured such that it will operate it reliably over all extremes of those three variables. Okay, so usually not all. For example, let's consider the operating temperature. Okay, so your circuit is usually designed, manufactured, verified, and tested within a range of operating temperature. Okay, so let's assume, for example, from let's say 5 degrees to 35 degrees. Okay, so that means if the circuit is practically operated outside of this range, like operated at like a zero, let's say minus 10 degrees Celsius. Then the circuit might malfunction because this operating temperature is outside of the temperature that the circuit is supposed to be operated. Okay, so practically it's very difficult to make sure your circuit operates reliably over all extreme environments. Okay, we usually make sure it operates at a relatively common environment. Okay, so for example, we will do a lot of testing or verification based on the tools. So for example, for the environment variation, we can use the tool to analyze the supply voltage and temperature. Okay, so for example, the supply voltage may vary, okay, due to the tolerance of the voltage regulator, IR drop along the supply fails or the rails. For example, the voltage is not perfect, okay, and the DIDT noise. The variation in supply voltage is normally like plus minus 10%. So the supply varies across the chip and in time. So that means, for example, at this time you are operating at like 1.5 volt. Next time you are operating like 1.6 or 1.3 volts. So it's possible. So we need to test it. We need to test the circuit for this range of the supply voltage. And another is like, as we mentioned, the temperature. So as the temperature increases, the drain current decreases. Okay, so we can use we call the thermal map to analyze the thermal or the temperature for throughout the circuit, and to analyze what will occur or why might occur for different temperatures. Okay, so we have to do this analysis. Okay. So this is another case we use the tool to analyze the IR drop, like the voltage variation analysis. So for example, you can see the different color represent different things. For example, in the color in red is the voltage is from 1.58 to this range. So you can see in this range, and then the range in this green. So you have another range of voltage. So you can see we use those tools to analyze the variations related to the voltages and the temperatures. Okay, and then this is also another example of thermal analysis. So we use this tool to analyze the temperature throughout the circuit or throughout the system. Okay, so and we have other variations related to the process. So for example, the threshold voltage. So the threshold voltage variation is caused by different doping concentrations and mobile charge in the gate and something else. And we have the channel length variation that is caused by photolithography, proximity effects, and deviations in the optics. So those are the variations you might encounter during the manufacture of your circuit. And we have the interconnect dimensions. This is caused by photolithography and the HM approximation effects. So that's also the effects during the process or the manufacture of the circuit. Okay, so then when we measure our circuit, so you can see that the threshold voltage variation, so the delta VT can vary. So it's not a strict temperature, so it's in the range. Okay, so for example, similarly for the VGS and the IDS, you can see the VT will be usually in a range. So it's usually not a fixed value, but it usually is it's kind of like a range. So we call this variation. Okay, and then so that means when we design a circuit, we usually need to verify and test the circuit to make sure they can operate it at different environments. So we usually call it design corners or corner cases. So we have we call a typical case, fast case, slow case. Then so you can see we have NMOS and we have a PMOS. So we are usually in the middle is we call TT, typical. And we have 4 different combinations, SF, that means slow, fast, fast, slow, and slow. So you can see this is usually this is a range. Okay, so ideally we operate at this TT, typical, so that's the center of this range, but actually we have to build up a variations parameter along with this center. So then we test with those 4 different corners. Okay, so that's why this is called corner. So you can see this is a corner, right? Corner, corner case. So that means if we test with this 4 corner case and the circuit operated fine, that means the circuit will be operated correctly within this range. Okay, then that should be okay. Okay. Okay, and then that's another issue is called the reliability. So the reliability issue is that the IC might fail, okay, at some time. So we usually use a metric to measure the reliability of the circuit. We usually call it MTBF, mean time between failures. So what's the average time between the failure of 2 times? So this is the number of device times the hour of operations divided by number of failures. Okay, so for example, when your number of failures increase, so if this increase, this will be decreased, right? So that means the time between failure will be decreased. That means you have failure at a more often time, right? And otherwise, if you, for example, if the hours of operation increase, that means this MTBF increase. That means the time between 2 failures increase. That means the failure happens less frequent, right? So that means you have higher reliability. Okay. So and we have actually in the industrial design or industrial management, we also have some other different kinds of approach to measure the reliability. Okay. So for example, the MIT, okay, so number of failures per million hours per device. So that's, for example, the 1000 FIT is good for a single chip. That means 1 failure at every 114 years. Okay, so that's another measurement to measure the reliability.